This declarative approach is key for automation and reliability. Within this pipeline, MLflow serves as the project's laboratory notebook. Every single experiment is logged. The exact code version, the data hash, hyperparameters, performance metrics, and the resulting model artifact. This systematic tracking is the difference between ad hoc experimentation and a scientific, reproducible process. When a model is ready, MLflow's registry provides a central, versioned repository. For actual compute, I leverage cloud platforms like AWS SageMaker or Google's Vertex AI. They provide the on-demand GPUs and distributed training infrastructure that would be impractical to maintain in-house. Finally, for serving the model as an API, I rely on frameworks like Selden Core or Kserve, which handle challenges like traffic splitting for A/B testing, canary deployments, and explainability right out of the box. This stack transforms a model from a file on a laptop into a scalable, enterprise-grade service. Pushing a model to production isn't the finish line, it's the starting line. A model's performance inevitably degrades in the real world, and our job is to catch it. This requires a two-pronged approach: monitoring and observability. For standard system monitoring, I use the classic combination of Prometheus for collecting time series metrics like latency, error rates, CPU, and memory usage, and Grafana to build intuitive dashboards to visualize them. This tells me if the service is healthy. But what about the model itself? That's where specialized observability tools are critical. I use libraries like Evidently AI to proactively detect silent failures like data drift and concept drift. Is the data coming into the model today significantly different from the data it was trained on? Is the relationship between features and the target variable changing over time? These tools automatically generate reports and visualizations that answer these questions. This is the core of observability. Not just watching predefined dashboards, but having the tools to ask new, deep questions about your system's behavior when something unexpected happens. Without this layer, you are essentially flying blind. So, we've journeyed from intelligent content removal to instruction-based editing, and finally to efficient model personalization with Dreambooth and LoRa. The trajectory is clear. We're moving towards ever-increasing levels of control and specificity. The next frontier is about composing complex scenes and exerting granular control over the output. Technologies like ControlNet are leading this charge. By conditioning the diffusion process on additional inputs like depth maps, human-posed celatons, or canny edge detection, developers can now precisely dictate the composition and structure of a generated image. This bridges the gap between the unpredictability of a text prompt and the explicit control of traditional CGI. Looking ahead, these principles are being extended to generate coherent video sequences and 3D assets. What this means for us as practitioners is that these AI tools are becoming less like black boxes and more like programmable visual synthesizers, fundamental instruments for anyone building, designing, or working with intelligent systems.